It's a few months now that I have a new machine in the shop. A small benchtop CNC lathe from the Austrian machine manufacturer Emco. The machine is about 40 years old, and although it's overall not in the worst condition, there are some issues which have to be addressed before I can really work with the machine. One of the first things I did was to restore the rusty chuck which came with the machine. The Emco Compact 5 has a pretty unique spindle nose, and by the time I got the machine, I was convinced that there are no new chucks available today for this mount. Given the price for even a used original chuck, I thought it's better to preserve the one I have and restore it to look a little bit more pleasant again. I started with the idea of a pretty fast and straightforward project, but as often, things went a little bit different, and in the end, but we came to that later. First, I unscrewed the chuck from the machine. And that is the rusty beauty before bringing it back to shine again. At first, I disassembled the chuck. It is very simple and consists only of a few parts. 3 jaws, the main body, the plane spiral, a disc spring, and the back plate. And of course, a few screws. And these are all the parts of the disassembled lathe chuck ready for restoration. After disassembling, I cleaned all the parts with isopropane alcohol to get rid of all the dust and dirt. As you can see by the color change of the isopropane alcohol, there was quite something to clean on this chuck. To get rid of the rust, I soaked all the parts in a bath of vinegar overnight. On the outside of the plane spiral, there are quite some burrs from the past decades of use, so I first cleaned the part carefully with a Proxxon IBS grinder and a steel wire brush, and decided afterwards to skim the outside diameter of the plane spiral with a light cut on the lathe to make it smooth again. Before taking the cut, I carefully dialed the part in. As the plane spiral is hardened, it is a little bit tough to machine, but with a new polished carbide insert for aluminium, it machined quite nice. I also cleaned the front surface with a small stone. While doing this, the other parts in the box of vinegar are ready for further cleaning. The vinegar did a great job of removing all the rust. I just had to brush away the residues and got nice and clean parts. Interestingly, the three jaws blackened in the vinegar, which I can't explain why, but in this case it is highly appreciated. After the bath in the vinegar, it is extremely important to clean, dry and oil the parts immediately, as they otherwise instantly start to rust again on the air. Don't ask why I know this. The plane spiral got a bath in vinegar too, and with a closer look I found out that first, the plane surface of the spiral is not even and parts of it are very rough, and second, from the back side you can see that there seemed to be a circular crack around the inner bore. I assume that this is a failure from the hardening process and is probably right there from factory. I can't do anything on the crack, just have to live with it and hope the part will hold up for the future, but I can clean up the plane surface of the spiral on the lathe. And that's what I did next. Again, I carefully aligned the part for both radial and axial runout in the forger chuck of my lathe before doing a really light cut on the front surface. And that is the front side of the chuck with a very nice surface finish now. To turn the back surface exactly parallel to the front surface, I used my new made split jaw chuck. This is a 3-jaw chuck with interchangeable aluminium soft jaws. I turned out the jaws to about the diameter of the plane spiral, which guarantees a very precise axial and radial runout of the part. If you are interested in how I built this chuck, there is a detailed video on my channel. With the modified chuck jaws, I can skim the second surface too, and as you see in a moment, it was not really parallel to the first one. Now I got two parallel surfaces with a really nice finish, but during machining I introduced some nasty markings on the inside diameter of the part, which ruin the exact fit. As the surface finish on this bore isn't spectacular either, I decided to turn it out and press a bronze bushing in. I ordered a 45 by 40 mm sinter bronze bushing to make the new plane spiral bearing from. To make space for the bushing, I had to turn out the inner bore. For doing this, I had to carefully align the plane spiral in the forger chuck again. Next, I modified the sinter bronze bearing for an interference fit in the plane spiral, so it can be pressed in later. I let the outside diameter of the bushing a few hundredths larger than the inside diameter of the bore in the plane spiral. short chamfer ring, and I can cut off the bronze ring. And that's how the new bronze bearing should be installed. I put the plain spiral in the oven and heated it up so that the bore grows, hopefully making pressing the bronze bushing in easier. I tried to press the bushing in with the help of the bench vise and some improvised big aluminium jaws, but unfortunately that ended up in a catastrophe. The bushing started crooked, I had to tap it out and press it in again. On the second attempt it worked, and luckily I could save the part. Now I just had to turn away the excess material on the lathe. And that's the finished plain spiral with the new bronze bearing. Problem now, I have to modify the main chuck body too for the new inside bearing diameter. The chuck body too needs to be precisely dialed in before I can bring the bearing seat to its new size. I don't know if it happened when I pressed the bronze bearing ring in, but somehow the inner diameter of the bearing wasn't consistent. The measurements deviated by a few hundredths on different spots. To correct for this error, I decided to lap the bore in to final size. I improvised an aluminium lap in the right size and carefully finished the bore. As you can see, the bore didn't clean up all the way round, so I guess the bearing ring was seriously deformed by the first and crooked try of pressing it in. Before assembling everything again, I had to carefully clean the parts first to wash away all the lapping compound. And now, the moment of truth. With the chuck reassembled and mounted back on the lathe, I checked the runout after the modification. But, ooh, that is a pretty excessive needle movement. Almost 1/2 of a millimeter of runout error, that is horribly bad. I really regret that I haven't checked the runout on the chuck before doing the modification. I totally forgot about that and have no reference now, but 0.5 of a millimeter of runout is definitely too much. On a closer look, I found out that one of the jaws doesn't even have contact to the part all the way to the front. The clamping surface is somehow crooked. Disassembled again, it became clear why. The jaw has a serious defect on the clamping surface. I have no explanation for this. This might be right there from factory, but in any case, it is not as the jaw is supposed to look like. I remounted the jaws and prepared the chuck for turning the jaws out. This has to be done under normal clamping pressure to guarantee the best results, so I improvised this clamping jig from a piece of brass tube. It has 3 cutouts on one side in which the jaws engage and clamp against, while still allowing a boring bar to pass through the inside. Next, I mounted a boring bar in the tool turret of the lathe, and then I realized that the machine isn't even capable of the spindle turning in reverse. The left-handed boring bar I mounted needs the chuck spinning in reverse to work, but the machine doesn't offer this. So I had to buy a new right-handed tool before I could start turning the jaws out. Again, I used polished carbide inserts for aluminium on the hardened steel of the jaws. Now I could take a few very light cuts until all the 3 clamping surfaces of the jaws cleaned up. The runout test after turning the jaws out shows quite some improvement, but instead of being almost perfect, as you might theoretically expect, The test shows different numbers on different clamping diameters. The numbers vary between a few hundredths and about 2/10 of a millimeter. But the maximum runout error was more or less on the same spot on the plane spiral, no matter which diameter was clamped. So I marked the point on the outside of the plane spiral and disassembled the chuck again. I assumed that the new made bronze bearing ring sits eccentric to the plane spiral. To prove this assumption, I decided to make a new bearing ring which compensates the eccentricity and can be mounted temporarily in the plane spiral to prove my theory. So I destroyed the bronze bushing ring and removed it again. Next, I turned this arbor and dialed it in to run untrue about the half of the maximum measured runout error on the chuck, which is about 7/100ths of a millimeter. Now I pressed on a new made bronze ring and secured it with super glue to turn the outside diameter to size. This time I only went for a light press fit. The new bearing ring is now eccentric on purpose, and when mounted in the correct position in relation to the plane spiral, both errors should theoretically cancel out each other. I marked the high and low spots on the plane spiral and the bronze ring to mount both together in the right orientation. This time I used my milling machine to press in the ring, which made the process much easier. With the new bearing ring, I assembled the chuck again, remounted it on the lathe, and bored out the jaws again. Now I got a somewhat consistent runout error of about 1/10 of a millimeter on different clamping diameters. But what has changed is that the error is now independent from the position of the plane spiral, but it is consistent with the position of the chuck body itself. The maximum is on the same spot in relation to the chuck body, no matter which diameter is clamped. This led me to the conclusion that the bearing surface of the chuck body itself is eccentric by about 1/10 of a millimeter. To have a reference when correcting this, I skimmed the outside diameter of the chuck with a very light cut to run perfectly true. Again, I disassembled everything and carefully aligned the chuck body in the forger chuck. Now I checked the runout on the inner bearing diameter, and actually it runs untrue by almost 1/10 of a millimeter. So I turned down the diameter until the surface cleaned up. Of course, the plane spiral has a lot of play now. Just for testing, I temporarily corrected the fit with a strip of 6/100ths of a millimeter thick hasback foil and assembled the chuck again. With the corrected bearing seat, the runout was way better, and with about 2/100ths of a millimeter at minimum, pretty acceptable. With this positive result, I disassembled the chuck again, and again aligned the plane spiral carefully in the forger chuck of the lathe to turn away the temporary eccentric bearing and correct the bearing seat to run true to the plane spiral. Now I needed a new bronze bearing too. As the bearing ring has to be thicker now, I had to order a new and thicker material. I turned the outside diameter to size and cut the ring off. Then again, I heated the steel plane spiral up in the oven and pressed the new bearing in. The inside diameter is still too small, so I chucked the part up on the lathe again and brought the inside close to the correct size before finishing the bore by lapping to get a close fit on the mating chuck body. After one last assembly and turning out the jaws, I should theoretically get a pretty exact running lathe chuck. But to my disappointment, that wasn't the case. I still got about 0.05 of a millimeter of runout error. Pretty consistent though, but too much for my taste. The error, again, was on the same spot in relation to the chuck body, and my first thought was to go through the whole process again. But after rethinking, I tried if it is possible to tap the chuck in a few hundredths to run true. The chuck has a little bit of play on the spindle nose, so I loosened the mounting screws a little bit, and after a few taps with a soft hammer, the indicator shows the success. The runout error shrunk to about 1/100th of a millimeter. That is an excellent number for a 3-jaw chuck. Now I could finish the chuck by removing the jaws and carefully sanding the front side and the outer diameter smooth. The backplate of the chuck received a light skim pass to get a smooth outer surface, and with that, all the machining and major work on the chuck is done. And this is the finished main body and the backplate. The last step before finally assembling the chuck again is to renew the bluing on the jaws and the backplate. I used a cold bluing liquid, which is applied with a brush and then washed away under water. And here are finally all the parts finished and ready for final assembly. I applied a little bit of grease on the mating surfaces for a smooth action. Et voila! The finished restored Emco chuck, looking as good as new, I would say, and working at least the same, I hope. Oh, one thing still left. The spindle nose is in a pretty bad condition too. So I brushed away the loose dirt and cleaned it with steel wool, Scotch-Brite and WD-40. I actually did this way earlier in the process, but for dramaturgic reasons I show it here. And that's the spindle nose, clean and shiny again, and ready for the newly restored chuck. And here comes the tragedy. What do you do with a chuck you invested hours and weeks of work into to make it function properly again? Right? You replace it with a factory new one. During the restoration process, I figured out that the chuck of one particular lathe from Proxxon coincidentally fit exactly to my Emco lathe. I contacted Proxxon and told them about my project and asked if they want to support me with one of their chucks. I'm glad to say they said yes and thankfully sent me this beautiful new 3-jaw chuck for me. You may ask what the new chuck can do better than the old one. The most obvious thing is that the original Emco chuck is, due to the drill chuck design, pretty inconvenient to use, and because of the disc spring, extremely hard to turn. The new chuck is just a joy to use, as it should be for a decent lathe chuck. It doesn't only look spectacular, it also seems to be extremely well made. Just one tap with the soft hammer and the chuck ran through better than 1/100th of a millimeter, and that without having to correct anything or boring out the jaws. That's how it should be. So again, my greatest thanks to the company Proxxon for this gift. I hope you enjoyed following this journey with me. Thank you all for watching, thanks to all the Patreons, and till next.